All right, good morning. Sorry I can't be with you this morning. But what I'd like you to do is I'd like you to start by taking out your ray tracing examples from yesterday. Particularly, I want to take a look at this first one more time because we're going to use it to develop an equation so that we don't have to draw a ray diagram every time. And so yesterday, we drew our three principal rays. We said this is a vector pointing to some spot on an object. There are rays going out from this vector in all directions, but we're going to look particularly at three rays, one that goes parallel to the optical axis and then it ends up refracting towards the focal point. We have one that comes through the focal point and is refracting parallel to the optical axis, and we have the one that goes through the optical center that doesn't refract at all. And we said that the image is the vector that points to the place where these three rays converge. Because if I'm on this side of it looking at it, right, my eyes, these are my eyes, trace back these two rays to where they think they came from, and they think the rays came from here, which is why an object, we kind of showed this happening yesterday, and it's even more, but anyway, this image would appear like it was popping out of the lens. If you don't believe me, right, it's not exactly the same thing, but let me get something here real quick. If that doesn't make sense to you, or you don't believe that something can pop out, again, this is not an image, or sorry, this is not a lens, but this was the curved mirror thing I showed you a couple days ago, and I look right here. You could see it even better if this was in front of you, but I can actually, this looks like it's floating here, even though it's not. It's an image because the different rays appear as if they're coming from here. And this is what's known as a real image. So a real image occurs when the rays actually converge like this. Okay, that's a review of what we did yesterday, and I kind of rambled there for a second, but that's sort of a review of where we're at yesterday. And this is again, this is a real image because it occurs at a point where the rays actually converge. We also on the back did an example of a virtual image. Let me just draw this real quick so that we can talk about it. So we drew a virtual image. We looked at three rays coming off of this one. And we said, what would your eyes see? Where would your eye think that this image was, right? And we said that, well, what you'd have to do is you'd have to, if your eye's over here looking at this, right, your eyes are going to trace all these rays back, and it's going to think that these rays are coming from way back here. So if I trace each of these back, so I'll trace this one back. I'll trace this one back. And I'll trace this one back. Our eyes think, mine isn't going to come out perfectly, but it's going to come out close. Our eyes think that all of these, I didn't draw that all the way. Think that all these rays are coming from back here. And so we say that this is an example of a virtual image. It's a virtual image because, again, there's no light at the location of this image. It's just our eyes are tracing back these rays, and our eyes think that the light came back here from behind the lens. Now, in a little bit, you are going to play around with the PhET lab So you're going to use your computers to be able to drag this object in front of and behind the focal point and see what happens to it. I just want to, though, so you'll get more experience with why this makes sense when you do the lab here in a minute. And then we're going to do a real lab, like a non-computer lab, when I see you next time, where we're going to actually see a lens creating both real and virtual images. So that's a review of what we did yesterday. Now, let's take a few notes real quick before you do your lab today. So when we talk about lenses, we have an image, which is a location where light appears to emanate from. So again, in this case, right? In this case, the image was here because the light appeared to be coming from there. In this case, the light appeared to be coming from here, so that was where the image was. So an image is a location where light appears to emanate from. A real image is an image located at a spot where rays actually converge. So this one here, let me see if I can get that in there without, sorry, I just have to show it to you real quick. This is a real image because the rays actually converge there. And then we have a virtual image, which is an image located at a spot where there are no rays of light. So again, this is a virtual image because there's no rays of light here. That's where that appears to be. That's where the light appears to be coming from, but there's no light back there. Other examples of virtual image would be when you look at your reflection in the mirror. That's a virtual image because, again, there's no light behind the mirror, even though your image looks like it's behind you. This here, this demo that we did in class, right, this is a real image because there is light here, right? I can tell there's light there because I can kind of poke where it is, right? There is light here. So this is a real image. Okay, the other two things that I want to give you right now, just so that you can get started on your homework, is two equations that we will derive later. One is called the thin lens equation, and basically this is a way of finding where an image is going to be located so you don't have to draw the ray diagram every time. And the thin lens equation is 1 over di plus 1 over do equals 1 over f. And there's a couple things. F stands for the focal length of the lens. And I'll show you what that is here in a second. Now, the focal length can either be positive or negative. Whenever the focal length is positive, it's going to mean that you have a converging lens. And whenever it's negative, it's going to mean you have a diverging lens. Now, di, or let's start with do first. Do stands for the distance between the lens and the object. So then di stands for the distance between the lens and the image. And again, this one can be positive or negative. Whenever it's positive, it's going to mean you have a real image. And whenever it's negative, it's going to mean that you have a virtual image. There's one other equation that you're going to use to solve problems, and that's called the magnification equation. And the magnification equation is defined as HI over HO, and we used that last class. We calculate the magnification, but the thing we didn't use last class is this turns out to also be equal to, again, we'll prove this later. We'll prove this not today, but it equals negative DI over DO. Okay. So from here, you should be able to do your homework. But that's not what I want you to be focusing on right now. So let me give you your to-do list for the rest of the period. So you are going to, number 1, do the PhET lab that you picked up. That should be finished before you leave. You'll turn it in. And then after you're done with that, you can start thin lens problems. On the syllabus. And I'll just tell you this, I will post, so on Schoology, I will post one problem worked out, so that if you have trouble with it, I'll post a video of me working out one problem so that you can use that on your own time. All right, so go ahead and get working on that. Again, you'll turn this in before you leave. Any extra time, go ahead and get started on this. All right, enjoy your day. I will see you on Thursday.